Welcome to episode 9. This is Dia, and we're doing sine waves and cosine waves. So there was this one image I posted on Discord about a dozen minus one pencils that I bought with a truncatable prime written on it. A friend asked me where I got it, and I showed them Numberphile's video of truncatable primes where they also linked where they buy the pencils that I got. Some days later, my friend made a video about truncatable primes, showing those pencils and explaining what the primes were. And even after, since that was a retrospectively long time ago, that friend asked me what the pseudo-focus of sin x is, with a greater than, comma, and a right parenthesis. And here I am, quoting him and showing this video to you, where I will be answering that question here. Now, throughout this series, you may have an intuition where a pseudo-focus exists when there is some sort of curvature. Generally speaking, x squared and e to the x seem to curve only once, therefore it has one pseudo-focus. X cubed seems to curve twice, therefore it has two. X to the fourth may seem kinda troubling with one curve and two PFs, but forget that for now. Now, if you look at the wave, you can see that there are seemingly endless curvatures, which must mean that there are infinitely many pseudo-foci. Moreover, that also means that our pseudo-focus finder, the 5-step rule, will have infinitely many answers. With that in mind, let us use the 5-step rule to find the pseudo-foci of sin x. Step 1. Find f prime, and f triple prime. One must know how the derivatives of these waves work, but fortunately they're nothing complex if you do not know what these derivatives are. Alright, the first derivative of sin x is simply cosine x. The derivative of cosine x is negative sin x, making the next derivative negative cosine x. These are our three derivatives. Now, before we use these expressions, I always have the tendency to shorten sine and cosine, where sine of x is capital S and cosine x is capital C, so they're easier to read in equations, making f prime just C, f prime prime just negative S, f triple prime just negative C. Step 2. Solve for x in the equation 3f prime prime squared equals f triple prime times f prime squared plus 1. Doing the f's and using our notation, we get 3c times negative s squared equals negative c times c squared plus 1. There are many approaches to this equation, so I'll start by cancelling the c's. Next, let's take care of the parentheses, where negative s squared becomes s squared, and the right hand amounts to negative c squared minus 1. Now, we transpose the c squared. Next, we know sin x squared plus cosine x squared equals 1, so to get this, we separate 3s squared to 2s squared plus s squared. Now, with a 1 on the left-hand side, we can subtract this to the right 1, making it negative 2. Now, we can divide the 2, leaving an s squared. Next, we then take the square root to get sin x only. We get I for sin x. That did not seem right. I said there are infinitely many solutions, but ironically we got ourselves a null and troubling result. Well, this algebra is actually me when I was solving this equation for the first time. And you know what the brutal mistake was? Cancelling the c's. The moment we got rid of the c's, first step, our countless solutions got banished to the imaginary realm, aiming our algebra to an aimless, non-real result. What we did is like solving a quadratic equation where you've boiled it down to two binomial factors, and like a fool, divided the factors to 0, therefore getting 0 equals 0. However, we don't really need to go do everything all over again. What we can simply do is at some point in our algebra, we can multiply the c to both sides and not cancel the c's, as much as it tempts C or me to cancel it. Let's jump to s squared equals -1, where we integrate the c's to the equation. Next, let's put the right c to the left, equating to 0. Next, we factor a c, where we are left with two factors, c and s squared plus 1. Now, we equate each factor by 0, making c equals 0 and s squared plus 1 equals 0. As we've learned the hard way, s squared plus 1 equals 0 gives us no real solution, ultimately leaving us with c equals 0 or cosine x equals 0. Similar to what I said, there are infinite x values that make cosine x equal to 0, like pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, and so forth. So what these numbers mean is that there exist normal lines on the points on x equals pi over 2, 3 pi over 2, whatever, where at some point in each line lies a pseudo-focus. And one thing to mention, notice that our normal lines are vertical. This is because the point each of them cross have horizontal slopes, and that fact will have some significance to step 3. Abruptly speaking of step 3, step 3's equation is x minus f prime x cubed plus f prime x over f prime prime x. Doing the f's, we get x minus c cubed plus c over negative s. Okay, this step is surprisingly simple and short-lived, because although not obvious, we simply substitute the c's to 0 because of the step 2 algebra that we did. This here simply leaves us with x. This makes sense because when we look at a normal line on sine x, which is vertical, we can see that our step 3 answer is just the x value that we got on step 2. Now, let's acquire the y value through step 4, where the equation is f of x plus f prime x squared plus 1 over f prime prime x. Converting this with shorthand notation, we get s plus c squared plus 1 over negative s. Alright, I guess for our first we can turn the c squared to 0, leaving us with 1 over negative s. Now, next thing is multiply the first s by negative s times negative s, where it becomes negative s squared in the fraction. If you know your trig, 1 minus s squared amounts to c squared, and because we have a c squared, the entire fraction collapses to 0. Interesting. Our y value? 0? It's just too simple to be true, isn't it? Like, am I doing something too simple it could be wrong? Well, fortunately, no. 0 is the answer to every step 2 value, which are infinitely many. Alright, now we just do step 5 where we express 3 and 4 into a point. But in spite of the simplicity of step 3 and 4, step 5 is in turn a bit complex than the step 5 of x cubed, x fourth, and e to the x. Alright, compiling step 3 and 4 values, we get pi over 2, 0, 3 pi over 2, 0, and etc. To make the etc. explicit, we simply generalize the x part. To do this, we notice that the x values skip count by pi to the next number, so our x values can be generally expressed as pi over 2 plus pi n, where n is any integer. In conclusion, our answer to step 5 is pi over 2 plus pi n, 0, where n is any integer, which are our pseudo-foci. Lastly, when we enable the normal map, we can confirm that these are pseudo-foci because they are on the cone's tips. But we are only halfway done. Sort of. How about cosine x's pseudo-foci? Well, they're not that different. One thing about pseudo-foci is that when a graph is moved to the right, so do the pseudo-foci of same distance. Same happens with right, up, and down. I could just drag this sine graph and the PFs remain the same relative distance from sine. This fact is reinforced when I enable the normal map, which also glues to the function without any weird change of shape. Now remember that cosine is just sine but move pi over 2 units to the left. Well, this also means that the pf of cosine is just the pf of sine but moved pi over 2 units to the left. Since it's pi over 2 to the left, then the x part of the pf's coordinate pi over 2 plus pi n subtracts to pi over 2. By the way, this subtraction applies to every pf of sine, so don't really mind the n. When we subtract, the coordinate becomes pi n 0, where n is any integer. And this coordinate expresses every pf of cosine. Let us conclude this episode with that conversation I brought up. So again, my friend asked me what the pseudo-focus of sin x is, greater than comma red parenthesis. And to finally progress that conversation, I replied pi over 2 plus pi n 0, where n is an integer. Next, I reacted to what the fuck? And infinite pfs, I said. Oh, weird. Then, like a nerd I was, I proceeded to show the normal map with the pseudo-foci on the cone tips. Whoa, that's cool. TY, smiley face. YW, smiley face. And awkwardly, that does it for episode 9. Interesting episode because sine and cosine have such simple values of pseudo-foci, with their y values aligning the x-axis and x values on the peaks and troughs. Overall amazing. That does it for episode 9. Thus, like sine and cosine, I wave goodbye.